2. Okay, so what we want to do is find the period first. This is period 2, and then we count over to column 2. So this would be that element, which is beryllium. Okay, so if I am looking at period 3, group 15, what is the symbol? What letter is the symbol for that element? Period 3, group 15. You have periodic tables at your desk, so you should be able to look there. Try and find that. That's going to be phosphorus, or the letter P, right? Okay, so that might be the kind of question I might ask you on a quiz. All right, let's try one more. Let's do period 4, group 7. Mn. Okay, now pay attention to what order I say it in. So if I had said group 7, period 4, group still means the column. Okay, so I could ask it in either direction, but look for the period first so that you don't accidentally go down. Okay, so that's how we label those. There are some groups that you need to know the names of. So we have our alkaline metals. And then next to it, a very similar name, alkaline, I-N-E, earth. Metals. So in talking about, and let me zoom in a little bit so you can kind of see what I wrote there. In talking about those groups, sometimes I would say group 1, sometimes I would say alkali metals, okay? More commonly, your book or your homework might refer to an alkali metal. I tend to go with just the group number. But you should know what those mean so you know where to look. Then across the middle, these are called transition metals. And they fit very neatly. All the transition metals fit this characteristic. And so this is one that also goes by the name the D block. That will make more sense later on in the semester. Those are the D block. The other two are what are called the S block, but since there's 2 names there, I'm not going to write the block. But sometimes you'll hear people say, what D block element? We're talking about the transition metals. All right, on the other side, you probably know this last column. What's that?
Note that. Do you have the ideal is each one?
I do not. I know sometimes Ori and Isla play with it.
Okay.
So ask.
Got it.
All right, noble gases. Sometimes people will call those rare gases. They're not really very rare. They're just kind of hard to identify because they're not very chemically reactive. But argon is the 3rd most common gas in our atmosphere after nitrogen and oxygen. So it's way more common than even carbon dioxide. And then next to it is the halogens. All right, so those are names that I might on a test or a quiz ask you about, which of these elements is a halogen, which of these elements is a alkaline earth element. Okay, so if you look at the periodic table that's in front of you, what halogen is the lightest? Now the lighter elements are on the top, the heavier ones on the bottom. So what halogen is the lightest? Fluorine. So I find that column 17, and I look at the top. Okay. All right. So all of these over here say metals. We talked the other day about metals versus nonmetals being important. One way is because they form ionic versus molecular compounds. They're going to behave differently. And so you might want to draw in this line. It has the name, the Zintelborder. You don't need to know that name. Everything, almost everything to the left of it is a metal, including the stuff at the bottom. These bottom two things down here, the purple here, down here, those are metals as well. And then everything over this way, for the most part, are non-metals. And then the ones that sit right on top of the line are brown here. Those are our semi-metals, and you can see there's two that sit right underneath it. So that's where I said almost everything to the left of it. So there's two, GE and SB, that are also semi-metals. SEMIMETA. Now, I'm not going to ask you too much about the semi-metals, but I might ask you, is calcium a metal or a non-metal? And so you should be able to say, well, it's way over on the left-hand side, it's a metal, or it's in the alkaline earth metal, so it must be a metal. Is bromine a metal or a non-metal? So you find bromine over here in the halogens, and you say, oh, that's over on the right-hand side. Okay, so down at the bottom, we have some questions about this. The middle and the left are metal. And the metals are going to form positive charges called cations. And the elements on the right, this is where we can see it. And I'm going to put up here upper right. We have that diagonal line. These are non-metals. And they're going to form a negative anion. So as you do your vocabulary, you're going to see ion, anion, cation. Those are going to be your vocabulary terms. So you got to know which one is positive and which one's negatives. So cats have pause, so they are positive. Anions, think of anti or against, that's negative. So we can form these cations and anions. How do we do it? What happens to an atom that it's going to become positive or negative?
One that's gonna become positive, it's gonna lose an electron, and then one that's gonna become negative, it's gonna gain.
So it can either gain or lose electrons, and depending on which one it's done, it's going to become positive or negative. Okay, so if we have something that is neutral, then protons is equal to electrons. And so normally when we just look at the periodic table, unless we're told otherwise, we just kind of think of everything as being neutral. If we know we're talking about ions, then we can figure out what the charge is by looking at how many protons versus electrons there are. So the charge is equal to the proton minus the electron. All right, so if I look at element 3, lithium, if it's element 3, how many protons does it have? 3. Very commonly, it will only have 2 electrons. So if I wanted to know what the charge of lithium was, I would say lithium is going to be 3 minus 2, and that's going to be positive 1. And the way that we write that is with a little number higher up on the right-hand side. That's called a superscript when it's higher up. So we would write lithium. And we could write +1, but in chemistry, often ones are invisible. So often you will just see lithium plus. Remember, however, that if it's more than 1, so if it's +2, +3, then you have to put the number. So we don't want to just say it's some kind of positive. We want to tell how positive it is. And if there's no number, we assume it's a 1. All right, so for the most part, when we talk about elements, this is all we're going to write. last half of the class, we're going to be talking about isotope symbols. Sometimes we need to be paying attention to specifically what kind of atom we're looking at, in which case we're going to give more information. But before we get there, let's take care of these last couple of things. Our atomic number, that sometimes is represented by the letter Z. What does that tell us about the atom? Protons. And because the protons live in the nucleus and because they are positively charged, this is also sometimes called the nuclear charge. So at the end of the semester, we're going to be looking at how we measure things about atoms very, very specifically. We'll talk about the nuclear charge at the end of the semester. That will also come up again next semester. Right now, we just need to concern ourselves with protons. Now, the atomic mass. This is something that appears in that box that makes up each element. The mass is going to have a decimal. It's never an exact number. And the reason it has a decimal is because the weight of all of our neutrons and protons and electrons is not whole numbers to begin with. And then we've got this whole thing called binding energy, which changes the mass a little bit. So even if they were whole numbers, then it wouldn't work out to a whole number. But also many of our elements have more than one isotope, which means that they might have a different number of neutrons. Okay. So for the atomic mass, what they do is they take a natural sample and they say, okay, for what occurs in nature, what is the weighted average mass? So we have an instrument called a mass spectrometer. And so measures mass. And basically what it does is first it pulverizes whatever we're looking at into tiny little bits. So sometimes it's like a few atoms together, sometimes it's individual atoms. And so it's going to pulverize it down to these tiny little individual atoms. And generally they're going to have some kind of charge on them. So as they're ripped apart, they don't carry their electrons with them. You know, some of them will be +1, some of them will be -1. And they send it shooting down this tunnel with a magnet. Now the magnet is going to make that charge move to one side. And how much it moves is going to depend on how much it weighs. So, you know, if you had a wind blowing at you as you were running, you might drift a little bit to the side. But if I have a semi barreling down the road with a wind blowing, it's not going to shift as much. Okay. So the heavier it is, the less it shifts. And they can figure out very, very precisely how much these individual atoms weigh. So they'll look at, okay, I got this huge number of atoms that had a mass of 12 point whatever. And then I had a small number that had some that were about 13. And then I had a tiny amount that were about 14. And so we're going to average that all out so that I know that when I'm taking a sample, roughly how much that weighs. But I'm not going to say 12 plus 13 plus 14 divided by 3. I'm going to say, okay, well, this is a huge number. So I'm going to multiply it by, say, 99%. And then I'm going to take this one and multiply it by, say, 0.9%. And then this one multiplied by 0.101%. Okay, so that's what a weighted average is. It's taking into account how many times it occurs. So what appears on the periodic table is a weighted average for the different isotopes. So it has a decimal partially because it's an average, but partially because even if it were just one isotope, it's not going to weigh exactly a whole number anyway. Okay, that's going to be this, what we were using called these nuclide symbols. And so sometimes that'll slip out. So if I say nuclide symbols, I mean isotopic symbols. Okay. Okay, so for our nuclide symbols, they're going to take this form. This X is the element symbol. So whatever's on the periodic table, we belong. So A is the mass. I'm going to put that in quotes because it's not really a mass. The mass number. That's what's important. It is a whole number, meaning no decimal. And that is equal to the most massive particles in the atom, the total number of those. So those are the protons and the neutrons. The electrons don't weigh very much. Remember, they're like the ping pong balls that you might be holding as you're weighing yourself at the doctor's office, like that. Those aren't going to make a difference. Okay. So this whole number is protons plus, I'm on the screen, neutrons. All right, so carbon, and this was kind of the example I was giving before, it's element 6, so it has 6 protons. And the vast majority of carbon atoms have 6 neutrons. So we would write, so we'd say 6 plus 6 is equal to 12. So that's its mass number. And we would write the element symbol carbon. We would write a 12 up here for the mass number and a 6 down here for Z. Now the 6 and the element symbol tell us the same information. So sometimes people just leave off Z because they're like, that's not adding anything new. Okay. But we're going to leave it on there for right now. If we're not told anything about the electrons, we assume it's neutral and we just leave it like that. If you've heard of carbon dating or radiocarbon dating, this is using a naturally occurring isotope that is radioactive, and that's carbon-14. So carbon-14 has 6 protons plus 8 neutrons. And its symbol would be written like this. And so if we were reading this, we would just say the name of the element and then its mass number. Carbon-12 and carbon-14. Sense? And then if we know it has a charge, we would tack the charge on. All right, I think that covers everything I wanted to cover there. All right, so for the periodic table, any of these things that we've talked about, I might ask you about a group and a period number and find the element. Or since we know the atomic number is telling us the number of protons, I might say how many protons are in an aluminum atom. Or if I said, okay, if something has 12 protons and 10 electrons, what is the charge? All of those kinds of things might be something that I would ask. Okay. Now, before we go on to the next thing, I want to talk about why we end up with some common charges. So if we look at element 10, it is neon and it is a noble gas. And it just turns out, and we'll get into this next semester why, but it turns out that atoms are very stable when they have that number of electrons. So our common charge of fluorine for -1 gives it 10 electrons. Oxygen in the next column over gives a -2. Did we go over common charges? We didn't go over common charges. Let's go back and do that. They end up with 10 electrons. And I was just getting to, we call those iso electron. That's the vocabulary. Okay, back to our periodic table here. I did this in a different order. The other class. Okay, the first two columns are super easy. It's gonna pop on in just a second. Column one, always +1. In fact, you almost never find column one as being 0. Column two is +2. It is more common to find that as being 0, but not always. There it goes. Okay, so alkali metals are +1, alkaline earth are +2. The transition metals in the middle can be a number of different things. So we're not going to put common charges with them. There are a few that are pretty consistent we'll talk about later. But for right now, we don't have to worry about the transition metals. Over on this side, noble gases don't like to make compounds. They also don't like to make ions. So they will always be neutral for our purposes. And then the halogens will commonly be -1. And the next column over, called chalcogens, which you don't need to know the name, but that's what the name is. The non-metals tend to be -2. So everything in green here, for column 17, the halogens can be -1. Everything in green can be -2 for the chalcogens. The ones that are lighter green sometimes will have different charges to them. So that's why we don't always say, oh, those are -2. But if you had to guess, it'd be -2. Okay, and the reason that happens is if I add one more electron to the fluorine, I get 10 electrons. If I add 2 more electrons to the oxygen, I get 10 electrons. They are isoelectronic. If I take sodium, which has 11 electrons, and I take 1 away, make it +1, it has 10 electrons. If I take magnesium and take 2 away, I have 10 electrons. Okay, so they are isoelectronic. They have the same number of electrons. All right. As I pass this out to you, there is no place on this for your name. So just write your name on the front, because if I don't tell you to do it right now, somebody's not going to remember it.
I know you said it was Wednesday, but the quiz says it's Friday.
Yes, I changed my mind. I'm moving it to Friday.
Okay, I was just making sure.
That's why I was saying I'm not going over stuff on Monday.
Well, yeah, that we ain't gonna be here, but yeah.
Yes, but I will go over stuff on Wednesday.
I was making sure.
For clarity for everyone, the quiz will be Friday, not Wednesday. Okay, so remember, get your name on the front of this. I'm gonna collect it on Friday. Make sure you have it there. This comes from a book that really likes to illustrate how and why we're learning things, kind of using that metacognitive approach to things. So it's going to talk about why do we need to do this, but what's important to you are these learning objectives and the success criteria. So if you want to know what you have to be able to do for your test, you're going to look at the success criteria. Use the atomic symbol to represent different isotopes and ions. I will give you protons, neutrons, and electrons and say, write the isotope symbol, okay? Given one or more of the following items, then find the others. And this is basically what you're going to be doing on the back here. So if you can do the back, you can do that next one. The last two, you can put X's on those bullet points. I am not going to ask you, actually the third one, I'm not going to ask you to calculate percent atomic mass. You should roughly know that the atom is way bigger than the nucleus. You don't have to know precisely how much bigger, but it is way bigger. There's some definitions down there. We've kind of gone through those. So we're going to flip over to the next page. On the next page, there's a model, which means that it is giving you